We present our paper, SkyEye, Self-Supervised Bird's Eye View Semantic Mapping using Monocular Frontal View Images. Bird's eye view maps have become an integral part of various autonomous driving pipelines due to their feature-rich yet computationally efficient representations. These maps capture distances to various obstacles in the metric scale, which makes them extremely suitable for downstream tasks such as path planning, object tracking, and trajectory prediction. Existing bird's eye view mapping approaches are trained in a fully supervised manner and thus require large annotated bird's eye view datasets. However, bird's eye view dataset generation requires annotated LiDAR point clouds, HD maps, and 3D bounding boxes, all of which are resource intensive and difficult to obtain. Some works use simulation environments to obtain the bird's eye view ground truth labels, but they suffer from a large domain gap between the simulated and real-world images. We address these limitations by proposing SkyEye, the first self-supervised learning framework to generate a semantic map in the bird's eye view given a single monocular image in the frontal view. The core idea of our approach is to generate a 3D voxel grid that acts as a joint representation for both the frontal view and the bird's eye view. This joint representation allows us to leverage the frontal view labels to replace the ground truth labels in the bird's eye view. Results show that SkyEye performs on par with the existing fully supervised approaches without relying on any ground truth data in the bird's eye view. Here is an overview of our proposed SkyEye framework. A single monocular RGB image is first processed by an image encoder to generate the corresponding 2D feature map. A lifting module then lifts the 2D features into a 3D voxel grid using the camera projection equation coupled with a learned depth distribution. This intermediate 3D voxel grid is then processed along the depth dimension to generate the frontal view semantic predictions for both the current as well as the future time steps. Predicting the semantics at future time steps enforces spatial consistency of the scene over time and allows the voxel grid to learn geometrically consistent features. The resultant model, however, cannot be used to generate the bird's eye view semantic predictions since the bird's eye view head is still untrained due to the lack of gradient flow through it during any of the previous phases. This limitation is addressed by devising a fine-tuning step that explicitly trains the bird's eye view head using the bird's eye view pseudo-labels that are generated in a self-supervised manner. This fine-tuned model can then be used to predict the bird's eye view semantic maps from a single monocular frontal view image. The goal of our pre-training step is to leverage the spatial consistency of the scene offered by various static elements over multiple time steps. We achieve this by generating the frontal view semantic predictions for both the current as well as the future time steps using the voxel grid of only the current time step. First, we use the voxel grid for the current time step T0 to generate the frontal view semantic prediction for the same time step. We then warp this voxel grid to the next time step T1 using the known ego motion and use this warped voxel grid to generate the frontal view semantic prediction for time step T1. We repeat this process for multiple time steps and penalize each of the predictions using the cross-entropy loss function. This training procedure enforces spatial consistency of the scene and allows the voxel grid to reason about the geometric context of the scene over time. The fine-tuning procedure accounts for the lack of gradient flow through the bird's eye view head by explicitly training the network using bird's eye view pseudo-labels generated in a self-supervised manner. First, we predict the depth maps for a predefined window of input RGB images using a self-supervised depth network. We then use the known camera intrinsics and ego vehicle poses to lift the frontal view semantic ground truth into 3D and obtain an accumulated semantic point cloud. We then orthographically project the 3D points belonging to static classes into the bird's eye view to generate a sparse bird's eye view map. We densify the sparse bird's eye view map by applying a sequence of morphological dilate and erode operations. Parallelly, we combat the lack of observability of the shape of dynamic objects by first clustering the accumulated point cloud using the dbScan algorithm and then fitting ellipses around each of the resulting clusters. The ellipse parameters can then be used to generate the corresponding instance bounding boxes. These bounding boxes are then overlaid on the densified bird's eye view map to obtain the final bird's eye view pseudo label. We evaluate our SkyEye framework using the Kitty 360 and Waymo datasets. We perform experiments to evaluate the overall performance of the model, the impact of model pre-training on the overall performance of the model, and the generalizability of the model across different datasets. We evaluate the overall performance of our model on the Kitty 360 dataset and note that our model performs on par with the state-of-the-art fully supervised approach POBEV while not using any ground truth supervision in the bird's eye view. To analyze the impact of model pre-training, we vary the amount of supervision in the bird's eye view between 0.1% and 100% of all the available bird's eye view samples. In this graph, SkyEye with pre-training is depicted using a solid red line, SkyEye without pre-training is shown using a dashed red line, while POBEV is depicted using a blue line. Both the SkyEye models are fine-tuned using the bird's eye view pseudo-labels, while POBEV is trained using the bird's eye view ground truth labels. We observe that our model with pre-training outperforms both the other baselines by more than 7 percentage points when trained using only 0.1% and 1% of the available bird's eye view labels. This indicates that model pre-training introduces strong spatial and semantic knowledge into the voxel grid and thus improves the geometric reasoning of the model. Lastly, we analyze the generalizability of our SkyEye framework by training it on the Kitty 360 dataset and evaluating it on the Waymo dataset. We observe that our approach generalizes significantly better to the Waymo dataset, outperforming the baselines by at least 5.63 percentage points. Here are some qualitative results from our model. For more information about our work, please visit the project page using the URL shown here. Thank you.